Welcome to our review of Unit 6 for AP Physics C. The sections you can see here, or we're going to look at, is going to be rotational kinetic energy, torque with respect to work being done, angular momentum and angular impulse. We're going to look at conservation of angular momentum, and we're going to look at rolling motion. The 6.6 involving the angular momentum of an orbiting satellite is pretty straightforward. We did the forces and energy of orbiting planets within our gravitational parts of units 2 and 3. And so if we look at a orbiting mass, then that would be considered to be a point mass that's moving in a circle when you do angular momentum. So we're going to disregard that section, at least for this video. All right, well, let's get to it. First thing would be 6.1, which is conservation of energy. It is very important that with conservation of energy, we write out the entire conservation of energy statement. In the Chief Reader's report, that was commented as higher levels of success across the board for students who listed out all the possible forms of energy and then crossed out the ones that weren't present, as opposed to skipping that step. All we're adding to this in Unit 6 is K-rot, which is, of course, kinetic energy due to the rotation. This is not instead of linear, it's in addition to it. So linear is the translational motion. That represents is the center of mass, or the pivot point, moving in a straight line, which we would call translational. That's the 1/2 mv squared that we know and love. It can either be rotating, or in addition to moving translationally, it can be rolling, where it is both rotating and moving in a line. So it can have either of these, or it can have both, as it does with a rolling object, because that rolling object has a translational speed and it's spinning around center of mass. In that case, we'd have to include both as separate kinetic energy terms. If we look at some quick examples here of how this is going to be applied. In this case, there's a ramp. It's a classic physics problem, so this would be a rolling object situation. In previous videos, we talked about how for a rolling object without slipping, the translational velocity is the same thing as the tangential velocity at the outer edge. I can let you look at that in more detail. If you have a question on it, let me know. But assuming we understand that, then our mgh we have at the top is going to be converted into kinetic energy at the bottom. Since it's both moving in a straight line, translationally, it has 1/2 mv squared, and rotating, it has 1/2 I omega squared. Since we want to create common terms with these like terms, right, so that we can combine, then we can replace the omega with v over r, or of course we could replace the v with r omega, since that tangential velocity is same as translational because it's rolling without slipping. So that would be for rolling. If we look at a disk example, notice that we wrote out the whole conservation of energy in both of these, and we have the potential energy of the block when it's starting off at some height. There's no potential energy even though it's at a height, because the pulley never changes its height. So the potential energy is only in the block 2. Afterwards, this block has descended down some height and is now moving translational. So it would have kinetic energy, linear, 1/2 mv squared, because it's moving translationally. The block is not spinning. The system also has this pulley here that has mass. So the pulley, once this has been allowed to move down some height h, the pulley is going to be spinning, but its center is not moving translationally. So it just has rotational kinetic energy for the pulley. And because the tangential velocity at the outer edge of the pulley, where the string is the same as the translational velocity of block 2, we can do, again, that replacement of the omega with v over r. Another common situation that you may see is a rod that can rotate, or in this case, it's static equilibrium. So the point of the previous Unit 5 video talked about how to deal with static equilibrium and how we do forces and torques when there isn't a well-defined pivot because it's not actually rotating. And as we progress through this, cutting the string, it's now allowed to swing. So a Unit 5 problem would be involving the angular or translational acceleration. And a nice add-on for Unit 6 would be something like this, where we're taking that same situation and we're saying, what is the angular velocity? Notice that this isn't angular acceleration, it's asking for angular velocity after following some angle theta. I'm going to use energy here, not kinematics, because we have to be careful. Kinematics was going to require us to have a constant acceleration or angular acceleration. which it does not have as it falls. And so we would have to use energy here in this situation. It's also the more appropriate thing here when we have heights or angles in exchange for speeds and velocities. That's the hallmark of an energy problem. I'll write out the entire conservation of energy statement. The only real nuance here that we have to be careful of is if we have a rod or some object where I'm not sure where to measure the height from, we always measure the height from the object's center of mass. So for energy, and in particular potential energy, where we have to define the height, we're going to be looking at the object's center of mass as defining what height it's at. So the center of the rod by this red dot here is going to move some height. I made a right triangle to define that height in terms of theta. And that's really the only major nuance here that we have from an energy standpoint. This pivot point is not actually moving anywhere, so there's no translational motion. This is a spinning object around a pivot, so it would only have kinetic energy due to its rotation. And as another example, we would have this marble that's rolling down a track and around a loop. And what we're trying to figure out is what height we're going to release it from so that the marble is just starting to come off the track at the very top of the loop. If we applied conservation of energy here, which I actually have listed here as step 2, I write out the entire energy statement, picking 2 points. I'm going to use the release point, and the top of the loop is my 2 points. That would mean I'm trying to solve for H naught. I'm going to run into an issue here because I don't know the velocity at the top, and I don't know then omega at the top. So that elicits then a secondary problem that I need to do, like a side problem. Since this is an object moving in a circle, then I'm going to do circular motion at the moment that it's at the top, letting Fn equal 0 to create that condition that we have where it's starting to come off the track. Otherwise, we'd have normal force pointing down because it points away from the contact with a surface. And that allows us to solve for the velocity at the top. Since it's rolling without slipping, I would know that omega then is going to be that translational velocity we have, or tangential velocity, at the top over r. So by subbing both of those things in, I can then solve for the height. In this final example here, we're going to be looking at what happens if we have multiple different objects and springs. So we have a cart here of mass m, and then those wheels it has, which are discs, are each going to be a quarter m. So 4 wheels will actually add up to a total mass of m for the wheels and m for the box frame of the cart. And so this cart is going to be released at a height h. It's going to fall down the ramp, and it's going to collide with a bumper or a spring of known k value. So we have to make sure we understand first and foremost the rotational inertia of this, right? We have to consider 4 objects that are rotating. Each of them is a disk with 1/2 mr squared, and we get our total rotational inertia. Notice it does not matter that there's the m for the frame because the frame's not rotating. That's also of importance here for energy. I'm writing out my whole energy statement. I know the car has a height, so that's mgh. I know the tires are also at that height, so that's how I got 2 mgh. At the very bottom, before it collides with the spring, the objects are all moving translationally, the tire, right, and the body frame, totaling 2 mass, moving in a line with some speed v. And the tires alone are rotating, not the body or the frame of the car. So that's going to give me that I value I just calculated, and then the omega. Now the omega, we can go ahead and use v over r using that same translational speed v because the wheels are rolling without slipping. And so that's another example of how we can use energy when you have a couple different objects, some are rotating, some are not. And of course we can use energy for the spring part as well and bypass that kinetic energy moment and just use the top versus when it's fully compressed to calculate how far it will compress. In 6.2, we're going to look at torque and its relationship with work. So in this case, I've juxtaposed the Unit 6 and Unit 3 equations that we can look at here. And so work is force times distance that the force acts through, times a cosine of the angle between the force and distance's axes. We don't really have a cosine component to torque. It's just going to be the torque that's acting then instead of a distance. We're going to use the angular displacement, or angle. We can also look at a calculus form of that where we're going to be integrating then instead of force with respect to a change in position x, we're going to be looking at torque integrated with respect to an angle that's turning through. We have kinetic linear. We already looked at how that has its counterpart with rotational. So we would also have work energy theorem where we know that the work done by the net force, which always is going to cause speeding up or slowing down, assuming that the force is parallel to the displacement, that would mean that it's always going to, the work done by the net force, go into the change in kinetic energy translational. That's work energy theorem. So we have then that same equivalent for torque. The work done by the net torque is always going to be set equal to the change in the rotational kinetic energy. So now let's take a look at some of the details of this in more specific. So we can look at gaining and losing energy as work being positive or negative, right? Just like with force and distance. Algebraically, we can simply just take torque times delta theta, assuming that torque is constant for all duration of that delta theta. If we're given a tau versus theta graph, then area would give us the work done by that. And if we're given, sorry, this is a typo, tau as a function of theta, then we can integrate that function using this expression here. If we look a little bit more closely at the work energy theorem in its angular version, then the work done by the net torque, as we said, is equal to delta k rotational. And one thing of particular note here that students often mess up is with rolling objects. So an object rolling down an incline, is there work being done by friction or not? So static friction is going to exert a force going up the incline, and that force actually causes this object to start to spin because that force exerts a torque. So is it doing work? Yes. However, because the work done by that friction torque goes into k rotational, it would be redundant to include both the work done by that friction and k rotational in the same equation. They would, of course, just subtract out. So we have to choose one form to use, either the work or we can use k rotational, which is the work at the end. So what we're going to use always for rolling objects without slipping and for pulleys, with that work done by the tension force on the pulley, we're always going to use k rotational instead of that for those situations. Another way you could think about it is we don't really ever do work done by static friction through an angle. We would only ever look at work done by friction if it was sliding through an angle with kinetic. So again, for rolling objects without slipping, we are not going to use the work done by static friction because we're using the k rotational where that work ends up in its stead, and to use both would be redundant. So this equation would work out to be exactly what we had thought about it to be prior to knowing anything about work done by a torque. And with angular impulse and angular momentum and its conservation, we need to first look at angular momentum for various different objects. And so really there's only two, arguably three different types of situations where we can have angular momentum being defined. And we have rotating objects, pretty straightforward. You have a spinning disc or a sphere, like spinning a basketball on my finger, for example, a rod that's spinning around a pivot point, a hoop. All of those situations are going to be rotating objects that have an I value, and since they're rotating, they have an omega. So this is following analogously to linear momentum, where linear momentum is equal to mv. So angular momentum, L, is going to be equal to I omega, the angular versions of m and v. If we go now to a mass moving in a circle, skipping number 2 for a moment here, then because this is rotating, it's a mass moving in a circle and has an I value of mr squared and an omega, we can use I omega for a mass moving in a circle. But since it's a mass moving in a circle, circular motion has a v tan. So we can also instead write the angular momentum as mv tan r. And I showed right here that those actually derive to be the same equation. So I always think of kind of circles as being a hybrid between linear motion through the tangential and centripetal components with rotational. They're kind of like a mix or a hybrid of those. You can look at it like in either perspective. A mass moving in a straight line which is not a mass moving in a circle, it's a mass moving in a straight line, so just something that's moving in a straight line, can be defined as having angular momentum with respect to some pivot point using MVR. There's much more details we can flesh out of this, but if we define R to be the perpendicular distance from the pivot point to the object's velocity axis, which I was calling here the line of motion, that's always the R that we can use in our MVR. This little r is referred to as the lever arm. If you want to derive why that is, you can see me or you can Google it. I did include it right over here. Happy to explain that. But that's really important that in these problems, if you have a mass moving in a line and you're doing angular momentum, we want to extend that velocity arrow along an axis and then look for where there's a perpendicular distance between the pivot and that axis that we drew. That's always the R value that we use for angular momentum. Angular impulse, we can just follow with what linear impulse relationships were. So net force times time is equal to the change in momentum. That's often referred to as the impulse momentum theorem, just like kind of like the work energy theorem, similar to that. So the impulse is F times delta T. We can set that equal to the change in momentum as long as that net force is the force that we're using. So likewise, if we have a net torque acting over some time, that can be set equal to the change in momentum of that object. We can also do calculus with that, just like we did with impulse in Unit 4. Conservation of angular momentum, again, we can use the template of linear momentum, which required, under the conditions that this was derived, that all objects are free to move linearly, meaning no external forces acting on the objects. The only force acting is the force between them when they collide, for example. And we would say then the total system momentum before has to equal the total system momentum at all times. So if we apply that to conservation of angular momentum here, that's going to be not free to move in a line, but free to rotate around a pivot point. So there's no external torques that are affecting its ability to rotate. And so the angular momentum of the system should be the same at all times. And so we pick 2 points to before and after to set equal to each other so we can solve for things. I'm looking at a couple examples here of multiple choice questions. Classic ice skater problem. We've got to make sure we have this down. An ice skater spinning with their arms out versus in, so if they're out versus if they're in, is going to affect the I value. But since they're free to spin around the pivot created by their skates where it touches the ice, then if the I value is smaller because they brought their mass closer to that pivot point, then the angular momentum to stay the same would require the person to spin faster. Smaller I value, bigger omega. So all we really need to think about whenever any problem's asking, is angular momentum conserved? Is really just that, is it free to rotate? So please make sure you have that down, because they'll ask all kinds of confusing things. Angular momentum is conserved if the objects in the question are free to rotate. No external torques. That's it. Same thing with linear momentum. If they're free to move in a line, no external forces, momentum is conserved. Kinetic energy, not so much, right? Because work can be done. So for example, to change the I value requires energy to be spent. There's a change in energy associated with changing the I value. You have to bring your arms in, which takes energy. So kinetic energy is not a guarantee that it's going to be conserved. In fact, conservation of energy is total energy, not kinetic energy. So in this case, it would increase because this ice skater had to change their I value, and that added additional energy to the system. In this classic example, we have a object origin right here as our pivot. The mass is moving to the left along the x-axis with some speed v, and we got to find the angular momentum. So I'm going to picture then that axis, a line of motion, and then the perpendicular distance would be from the origin to this point here, which would be a distance a, and that's why it's MVA. In this example here, we have a skater that jumps onto a longboard. So they're asking about, is momentum conserved? There's no outside forces because it's on frictionless ice. So therefore linear momentum is conserved, and because they are free to rotate around their center of mass once their combined center of mass after the collision, then angular momentum is also conserved. In our last example here, this is a tricky one. We have a object that collides with this rod. It's a glancing collision, so although it was horizontal at first, it's going to come off with a speed v at an angle theta initially. And we got to use angular momentum here because the collision involves rotation. So in this problem, I would need to create an axis for that velocity arrow and then identify where there's a perpendicular distance between the pivot and that axis that I drew. And that ends up being this distance right here, which I can set up a right triangle to solve for, and it would be L cosine theta of that angle. Thanks.